Remember that. Today, we're happy to have for the brown bag Qianshu, who is a postdoc here and has been for a month and a half. Yes. So, go ahead.
Thank you. So very happy to be here today. Since I visited NYU last spring, I was really fond of the brown bag format, a talk that is with the explicit purpose of making it accessible to a wide audience. I'm very happy to be able to contribute my part. So today I'll be talking about some work I did with my collaborators where we explore the cosmological consequences of Nelson-Barr models in light of recent results about the stability of parity domain walls. So this is, as is hopefully obvious from the title, is a story about intersections between cosmology and particle theory, which is my main research focus. But as I hope will soon be clear, this is also a story where some phenomenological concern has motivated about thinking about these exotic objects. And it turns out that we require some input from formal theory or quantum gravity to understand properties of these exotic objects. And in turn, these understandings have led to new phenomenological understandings, which I'm really fond of this project because of this phenomenological informal interaction, which I think is kind of getting there. Okay, so now before I start, I just want to talk about my plan for the talk. So because it's a brown bag, it's supposed to be accessible, and I want to explain the necessary background as clearly as I can. But of course, from the title, you can see there are two big areas where perhaps some introduction is needed. First is Nelson-Barr mechanism for this one CP problem, and another is the whole sector, the whole study of topological defects and their cosmology. Now, I do not expect to be able to go through both of them in a thorough way in an hour, so I have made the decision to start the story or start the introduction from this side. The main reason is that, as I mentioned, the results about the stability of parity domain wall is new. So it's just a recent paper by Matt Reed and Jake Mahimura. On the other hand, Nelson-Barr models, the history is long, and there are many excellent reviewed papers. So I thought it's better that I spend some time explaining the more recent results. Now, but before I do that, I'd just like to spend 5 minutes explaining the whole story in a very high-level perspective. Okay, so at least we have some kind of bigger picture in mind before I dive into the specific of parity domain walls. Okay, that's a very long introduction, but let me start. So the whole story in 5-ish minutes. So I think I mentioned that Nelson-Barr models is one sector of solution to the strong CP problem. What is the strong CP problem? Strong CP problem is referring to the observation that there are two possible sources of CP violation in the quark sector of the single model. The first is the complex phase in the CP matrix, which is observationally about order 1. So in this talk, I'm never going to be talking about numbers with specific digits. It's all going to be quite qualitative. On the other hand, so this has been observation confirmed to be order 1. On the other hand, we have another source of CP violation called theta-bar, which is this specific combination of parameters in our Lagrangian. So this is just the argument of the determinant of the mass matrix for up-type quark, down-type quark, and theta parameter is a term in the QCD Lagrangian we can write, which has this form. The specific form, if you have never seen this operator, the specific form is not terribly important. But the important observation is that experimentally theta-bar has been constrained to be less than 10 to the minus 10. So within the quark sector, we have two sources of CP violation with vastly different orders of magnitude, according to experiment. And this is the strong CP problem. And in terms of solutions, well, possible solutions to the strong CP problem have been known for a long time. And roughly, they can be separated into two sectors.
Sorry, what is this delta?
Oh, where? Oh,
I know
sorry.
what is theta, I don't know what is delta.
Sorry, no, by delta I just meant the complex phase. I'm trying to not write theta because I already have theta on this side. So by this delta, I just meant the phase e to the I delta CKM in the CKM matrix.
And this is exactly what I don't know, and I'm afraid many of my astronomy friends neither.
Yes, so the CKM matrix is referring, is a 3 by 3 matrix. So there are 6 flavors of quarks in the standard model.
So this is the matrix between what, flavors and mass eigenstates, or what?
Oh, yes, exactly.
And
So-
one of the angles there is called delta.
One of the single physical
One of the
component-
phases, sorry, is called
There's
delta.
only one physical phase, and it's called delta.
And this is responsible for CP violation.
Yes, like in the Wheaton direction.
And this is an experimental fact.
Experimentally verified fact.
What
Same-
does it have to do with this axiom, with the state thing?
So these are two separate. So in the quark sector, if you write down the Lagrangian, there are in principle 2 places where CP validation can occur. They're independent sources of CP validation. But this one is the CP validation in the CKM matrix, experimentally observed to be order 1. This is a different source of CP validation in the PCB. So far, in principle, it can be anything. It's again an angle, so it can be between 0 and
So far we have only upper bounds for this thing, and we have a measurement for delta.
yes.
Okay, good.
Yeah.
Well,
And the
thank
strong CP problem is referring to the fact that we have to measure something order 1 here, while this is ridiculously small.
But that's not like, it's not inconsistent in some
not
way.
inconsistent.
It's
It's
just
just a fine tune.
strange.
So you can view this problem from 2 perspectives, which is also how I would categorize solution to the strong CP problem. The first perspective is that you say a CP is not a symmetry of nature. Now in this case, what do you expect? Well, when something is not the symmetry, and I have some parameters, they are both naturally between 0 and 2 pi. So what you expect without fine tuning is that the CKM phase and theta bar should both be order 1. Since it's not a symmetry, I don't have control over how much CD is broken. Of course, this is not what we observe. So the solution is to promote a theta parameter to the dynamical field, which I think everyone is familiar with, the axion. And the axion is going to dynamically relax theta bar to 0. So what that means is that the axion is going to get a potential from QCD dynamics, and that potential has the exact shape such that the effective theta bar you observe is 0, even though you started with a parameter that's not 0.
Just a comment
Yeah.
that in a way, this huge hierarchy between theta, bar, and delta is seemingly inconsistent unless you promote theta to a dynamical variable, because there are mechanisms that would feed from the CKM matrix into the coefficient theta within the standard model. So the CP problem is the question to which we do not have a good answer. Why the existence of delta of order 1 does not propagate to a significantly larger coefficient of the GG dual. Okay. So there is a problem.
The standard model that effect is tiny.
Yeah, I thought the
So we need to explain why it's so tiny.
so right.
Because you would expect it to be larger, but it's tiny and nobody understands why it's so tiny.
But what you mentioned, if you start with standard model with boundary condition that you set, theta bar to 0, then you generate, just by standard model RG, you generate tiny contribution.
It's a 3 loop and it's suppressed by the Yarlskog invariant, this famous Mary Kay.
It's many loops,
Yeah,
right?
seven.
Seven
Seven.
loops.
But now they compute. So in the axion potential, what sets the 0 point of the axion potential to 0? Or in
Ah,
other words, just saying
yeah.
that theta is a dynamical variable, we could still have a bare theta term. So what tunes that away?
So if the axion interaction is only generated by its anomaly with QCD, it has been shown that it relaxes with CD even further. But if you have anything, well, but that's the axion quality problem.
Well,
If you have something that's
QCD is without theta is parity concern.
Right.
So the potential will certainly have a stationary point at theta equals 0. It depends whether it's a minimum or a maximum. It turns out to be a minimum, 50% chance.
but there is a quality problem that you don't. The axion is a boson boson of a U1 Cauchy-Quinn symmetry, and you need to protect that symmetry from breaking from other sources.
Going back to your point, I thought if I remember correctly, if you calculate the contribution, the theta from delta CPM, that's way below the 10 to minus 10.
Yeah,
right?
yeah.
It's
In the
negligible.
standard model, yes.
Yeah.
But as soon as you try to imagine a theory where you explain that you can't have to a standard model, you unavoidably generate theta large.
Very curious as to what this other arrow is pointing to.
Okay, yeah, so here this perspective is that CP is not a symmetry of nature, and this is the axion solution, which I think everybody is more or less familiar with. But of course, you can again also take a perspective that I impose that CP is a symmetry of nature. And here, what you expect, or at tree, or I should say, at tree level in the Lagrangian, I should have both of these CP valuation to be 0. Of course, to be consistent with experiment, you need to generate order 1 CKM phase. But what you do is that you say CP is spontaneously broken. CP is spontaneously broken at some scale, which I call lambda CP, or some energy lambda CP, and this generates a delta CKM. That's order 1, and without spoiling theta bar. So first model of this sort was written by, oh sorry, this solution was first written by Qianshu and Quinn in 77. Reference is correct. And first model of this sort is written by M. Nelson in 84, and very quickly generalized by Barr in the same year. So now they're called models in this regard are called Nelson-Barr models. So, of course, based on the title, I'm going to be focusing on the Nelson-Barr sectoral solution to the strong CP problem. Even from the very brief description, we see immediately that Nelson-Barr models necessarily require spontaneous breaking of a discrete symmetry. CP, which is a discrete symmetry. And I'll explain this in much more detail later, but what happens when you spontaneously break a discrete symmetry in the early universe is that you would have production of domain walls. Which I will call DWs, because I will be talking about domain walls a lot. And now it turns out, well, first here you might say, well, this is slightly weird, because parity, even the charge conjugation is an internal symmetry, is something that only acts on the field. Parity is the space-time symmetry. It's supposed to be talking about flipping the spatial coordinate, the sign of the spatial coordinate. So how can we understand the spontaneous breaking of CP or the domain wall coming from CP?
Can I have attention, please? Can I have attention, please? To file safety director with an important announcement. announcement. We've concluded the work on the fire system, so at this point, if you see or hear anything related to the fire alarm system, please act accordingly. Can I have your attention, please? Can I have your attention, please? Fire Safety Director with an important announcement. We've concluded the work on the fire system, so at this point, if you see or hear anything related to the fire system, please act accordingly. Thank you.
So even though the Nelson-Barr model, as I said, have a really long history, turns out that these domain models coming from spontaneous breaking of parity hasn't really been understood until recently by Jake McNamara and Matt Reeves. And what they found is that unlike domain walls from breaking of internal symmetry, domain walls from spontaneously broken parities are absolutely stable. I will quantify what I mean by that very soon when I go into more details of domain walls. But so what that means is that once we spontaneously break CP and produce the domain walls, there's no way to get rid of them other than inflating them away. And we need to get rid of them to recover viable cosmology. We do not, the current cosmological observations are not consistent with a universe filled with domain walls, which I will also explain very soon. So what that means, very pictorially, if I have a scale of energy and I'm spontaneously breaking Nelson-Barr at some energy, which I call lambda CP, the result tells me the Hubble of inflation has to be roughly below that scale. Yes.
Is it possible to have a situation where CP is only approximate? So say corresponding to a theta bar of order, say 10 to the minus 15.
Yeah.
Okay, and then there is a certain amount of spontaneous breaking.
Yes.
That seeds the big delta.
Right.
And what would happen in that situation?
Yes. So, yeah. So there's always the question of can you explicitly break the symmetry that you want? And of course, in this kind of setting, what you need is to have a controlled breaking of the symmetry, because we needed the symmetry to do something in the first place. And it's unclear how we don't actually have a mechanism.
Oh, you need the UV completion. I mean, you need a picture about the UV completion to make this concrete. That's clear.
Yes, and unlike internal symmetry, I would argue that there is no, as I would argue very soon, parity is going to necessarily involve the topology of the underlying manifold. So it's intrinsically something. If you think about breaking, I will argue that you need to think about quantum gravity or to have a controlled way. So unlike internal symmetry, such as we can protect the global symmetry by having a set of gauge symmetry such that I forbid renormalizable operators, that's one way to protect global symmetry. Or I can protect global symmetry, for example, the chiral symmetry breaking QCD. It's a good symmetry because the mass of the quarks are small, but that is compared to the QCD scale, but that is given by the smallness of the Higgs web, which is kind of, I would argue, is kind of accidental. And there isn't really a mechanism to protect the space-time symmetry from the QFT perspective, other than just tuning the CP validating parameter by hand. That's why I'm not going to the perspective of controlled explicit breaking of systems.
So you're saying there's either breakdown of order 1
Yeah.
or exact. There's nothing in between.
Well, I'm not aware how to do it in between. Unlike internal symmetry where everything is controlled in a QFT.
Sorry, for instance, in QED,
Yeah.
parity is an accidental symmetry broken by small effects, because at the level of dimension 4 and less operators,
Yes,
you
yes.
cannot write any operator that breaks CP. And then the next, or parity, even parity, let's say parity, and the next operator you can write down dimension 6 breaks it. Which this is why parity is a famous symmetry in low energy physics, just an accident. So I'm just thinking whether you could have a situation where the standard model emerges, where there is a separational scale like there is between the standard model and QED,
Yeah.
the QED scale,
Yeah.
where parity and CP emerge as accidental symmetry. very much like they emerge in QED.
QED.
What QED parity is an accidental symmetry. Problem by small effects. Dimension 6 operator from Z boson exchange. While the interaction with photon and the electron mass do not break the symmetry, which are the two parameters that determine QED is M electron and alpha. Those don't break. Just by accident,
Yeah.
you cannot write it's the same, it's an accidental symmetry.
I see. I would need to think about that case a bit more. Yeah. Thank you. Yeah. Although I would, if I have time, I would be talking about something very similar, like the idea you mentioned, even without having to explicitly break CP. But sorry, where was I? Yes. So if I take the perspective that CP is a symmetry of nature, then based on the recent result, I need to have inflation below the CP scale. Okay, that's a specific deal. The slight deal is that turns out that this scale of CP breaking, you're not allowed to take it arbitrarily high. So now this scale is constrained from above for the quality problem of Nelson-Barr. And simply put, it's just a statement that if you take the CP breaking scale to be very, very high, you're actually going to spoil the solution of Nelson-Barr. You're going to generate large correction to theta bar, and you will not be solving the strong CP problem. So you have a constraint on the scale, and in the minimal model, turns out that lambda CP has to be less than 10 to the 8 GeV. And for people familiar with cosmology, you will immediately notice that this is much, much smaller than on the Hubble of inflation, experimental bound on the Hubble of inflation from bicep tech, which is around 10 to 13 GeV. So
this is because you break CP by a scalar field. And this is from dimension 5 operators contributing to theta.
oh yes. So
Clark.
yeah, more model building would push it up. Right. So this is, of course, this is a statement that's specific to Nelson-Barr model building. Nevertheless, it's a new cosmological signature of Nelson-Barr models, which traditionally really didn't have any phenomenological consequences. Without this connection, I generate some new physics at very high scale. They're outside the reach of colliders, and previously people thought there are no cosmological.
Sorry, how do we know that H inflation is greater than 10 to 13 GeV?
Oh, sorry. This is the experimental bound from non-measurement of tensor to scalar ratio.
So it is smaller, not greater.
Oh, smaller. It's smaller. Yeah. So sorry. I meant 10 to the 8 GeV is much less than the current upper bound on Hubble.
So we are okay.
Yes, yes. There's no experimental contradiction.
Okay, so there is only upper bound.
Yeah.
Okay, good.
There's no experimental
Upper
contradiction.
bound from gravity waves. That's easy, of course.
Yes. But I'm saying that this bound is significantly stronger than the experimental
Oh,
bound.
because lambda is ledged the nature, it
Yeah.
cannot be inflated away. Okay,
Yeah.
good. So you do have a problem. Okay.
Yes. Or it's pushing it a lot lower
Okay.
than the experimental bound. And our work is just to explore these consequences of imposing that lambda CP must be greater than Hubble of inflation, or Hubble of inflation must be less than lambda CP.
So Nelson-Barr is wrong. What's the problem?
It's not a problem, but it is a potential solution, and you're free to say Nelson-Barr is wrong, and then we can. But there are. I'm not going to.
You will wiggle out. Okay, good.
Yeah, there's a way to wiggle out of it. I'm definitely not getting to Nelson-Barr, but hopefully I will explain stability of parity domain walls. Okay, so now
There's
that's
a question.
Yeah. Oh, sorry.
Sorry.
I am a bit lost on the question that we want to answer with all of this stuff.
The question we're trying to answer.
Yeah, like what's the question?
The question is that there is this well-known solution to the strong CP problem called the Nelson-Barr models. So far, they are thought to have no cosmological signatures. There's no, you can assume it's true and leave it. It's also one of the reasons why they're kind of understudied compared to axion models, where there's some very clear, cosmology, axion can be dark matter, axion can do that, axion can do this. While on the Nelson-Barr, it looks like it didn't really have anything to do with cosmology, and there's also out of reach of colliders, and now we're saying there's like, maybe it's not that spectacular, but at least there is one thing that ties Nelson-Barr model building with cosmology. Yeah, and there is some signatures where, unfortunately, it goes the way of if you observe something, you disapprove this type of Nelson-Barr models instead of the other way around. We're not going to be able to confirm Nelson-Barr from cosmology, but at least that's something that we didn't know before.
So a quick question: is there any way to set a lower bound on H inflation that's reasonable?
Oh, H inflation. Well, I think anything. Yeah, that's the unfortunate thing. I think anything that recovers, as long as we have radiation dominated universe by DBN, we're like fine.
I see.
And that's one entity. Yeah.
Sorry, I didn't know.
No. It's a good question, but that's the status. It's a bit unfortunate, but that's the status. Okay, domain walls. Okay. So before going to domain walls from spontaneous breaking of parity, I'd just like to explain domain walls from spontaneous breaking. Of the internal symmetry. So throughout, I'm just going to assume very simple Z2 where I have a scalar going to the minus. It's a symmetry. I assume there's a symmetry in my theory. So, for example, a potential in this form respect my symmetry. Everything is a square and quadratic. Of course, if you draw the potential out, you will notice that the potential has two minima, which I'm just going to call V as position phi equals to V and phi equals to minus V. You can solve for V from mu square and lambda. I'm just not going to write down the expression. It's not terribly important. You'll notice that the vacuum is not does not respect the symmetry. Right? If I sit in the vacuum here, I do the Z2 symmetry, I'm going to move to the other vacuum. And that's just the definition of the symmetry being spontaneously broken. Now, in the early universe, actually what's going to happen is that when the temperature is much, much higher than the scale in the theory, I'm going to have thermal corrections that restore my symmetry. So my potential is it's actually, due to thermal correction, it's going to look quadratic when the temperature is very high. And as the temperature pulls, it is going to go into this wine bottle form. So this is what happens when temperature drops. Okay. Now the universe is big. So as the temperature drops, the field was initially sitting here, but now it's like, okay, now I have actually different minima, and I want to roll down into the minima to minimize energy. Of course, the universe is big, so I can have totally causally disconnected regions where on one side, one region, my field is like, okay, I will fall into that minimum, and in the other region, the field falls into the other minimum. And because they're causally disconnected, there's no way for them to talk to each other and align their perspectives. You're just going to do whatever they wanted to do. But of course, we cannot have discontinuous field configuration across space. Like everywhere, the field should be continuous, so we don't have infinite gradient. So what that means is that as a function of position, my field configuration at this place is fixed to be minus V. At this place, I'm fixed to be V. I need to continuously connect them. And you can do this. You can find out how they continuously connect by trying to minimize the energy, it turns out it just looks something like this. It should be symmetric. Sorry about the horrible drawing. Slightly better. Okay. So that turns out to be the field profile, and as is natural to continuously connect from minus V to B, the field had to cross phi equals to 0, which was this top point. So the field configuration had to interpolate across the hill. So what that means is that there is, in this region, there is some pretty high energy density here. Pictorially, if I come back to this picture, it just means that between the region of phi equals to minus V and phi equals to V, I have a wall of energy separating them. And this is the domain wall. It's a two-dimensional, roughly two-dimensional structure. It's very big and very thin. And so I can try to characterize domain wall by its energy per area, which is across a wide range of models, it roughly scales as a cube. It's the only scale in the theory, and the energy per area is a cubic.
Is it an actual structure or like an abstract?
Oh, it's an actual structure. There's like energy density. It moves around. Yeah, in the
Actual but non-existent.
So there are domain walls in real systems.
Yeah. In like solid state.
Yeah, because they're real, is a real phenomenon.
Yeah. They have nothing verified to exist in ordinary universe, but they exist everywhere in space matter. We're still waiting to discover things like this. Okay. Okay, I'm going to
Tell us how you solve lambda less than h.
well, you wanted to hear.
Didn't you just rule out Nelson-Barr because actual h is greater than lambda?
Sorry, I think I confused all of the people with this. So my Nelson-Barr model says Hubble of inflation should be less than lambda CP, which can be in minimal model. I'm going to take it to be 10 to the 8 GeV. I mean, my current experimental bound says Hubble of inflation is less than.
Oh, Hubble is less. Okay.
Yeah, there's
so
no.
Hubble
there's no
can be less than lambda. That's
yeah.
fine. Okay, sorry.
But the consequences of pushing it below 10 to the 8 is kind of drastic. Or there are signals that only exist in here. So if you observe something.
So the interesting part is this Hubble is actually less than 10 to 8 GeV in order for this thing to work.
Yes.
Okay.
I think that, yeah.
So if tomorrow they discover gravity waves at the level of 10 to minus 7, you are out.
Minimal Nelson-Barr is out.
Okay, good.
Yeah. Okay. And yeah, the reason that we need to get rid of this, I'm just going to skip the explanation a little bit, is that, if they are absolutely stable, they're going to stay until today, and the observational CMB, etc., is not consistent with a universe filled with domain walls. Okay. So to get rid of them, so they might be produced in the early universe, but if we have a mechanism of getting rid of them, of course, we can be consistent with cosmological observations again. And the way we can get rid of them, again, I'm going to assume that the symmetry is exact. So with the exact Z2 symmetry. Now if the symmetry is global, if Z2 symmetry is global, there's nothing you can do, right? If it's global, it's saying that the state where phi equals to V and phi equals to minus V are different physical states. I have a symmetry that relate them, but they're a different physical state nonetheless. Okay. So if I have a domain wall separating the two physical states, and it should be there. I should not be able to open a hole and get rid of the domain wall, because then I would have two distinct physical states separated by nothing, which is inconsistent. So if Z2 is global, the domain walls are just stable. But if Z2 is a gauge symmetry, now I'm saying that the state phi equals to V and phi equals to minus V are actually gauge equivalent. So they're actually the identical physical state. So you might imagine there's some way to dynamically open a hole in the domain wall, because I should be free to extrapolate between identical states. Yes?
I'm confused now because the standard law in particle physics is that you cannot spontaneously break gauge symmetries. So how does it work?
How do you mean?
Well, there is a theorem which had been
Elitzur's
published many
theorem.
years ago by Elitzur, which explains that local symmetries cannot spontaneously break, and it's a very simple argument in the tunneling between, I mean, the reason you can't have spontaneous breaking of a global symmetry is that it's difficult to flip all the points in space-time simultaneously to go from one to the other and mix. But if you have a local symmetry, that's easy. That's a final tunneling probability. So it's a well-known law in particle physics that you cannot spontaneously break local symmetries. So then I'm confused how this scheme is supposed to work.
Then I'm confused. There are definitely, I read that paper like ages ago. I don't remember anything, but there are definitely systems or the Higgs, for example, the Higgs mechanism, where the physics is well described by viewing the gauge symmetry as being spontaneously broken and Higgs getting embedded. So I don't know
That's a way of speaking, but the symmetry is.
But for this global Z2, if you take the product of two scalar fields at different points, this is gauge invariant.
Yeah.
And if you are at left and right of a domain wall, if there's no domain wall, the product will be 1. If there's a domain wall in between, the result will be -1. Okay, just
yeah.
So in a sense, there is a non-local quantity that can distinguish, can tell the presence of a
The
wall.
whole idea was to use a local symmetry to avoid.
No, this is not local. This is gauge, but global. Still is it? Oh, you say this is gauge local. I think this is. Is it global or local?
I'm going to gauge it now.
No. Okay, gauge is, but it's going to be local or global. You can gauge a Z2. Are you saying this is going to be local?
Do you mean local? I think is there.
Well, there is a Z2 at every point, independent.
Yes. But the gauge, I don't. Sorry, the argument of formation of the domain wall. I definitely have separate regions due to those finite causal horizons. So I can fall into different calculus.
Yeah. Okay. Maybe.
But okay.
All right. Maybe we should talk after this.
Okay.
But it's a subtle technical point.
Yes. Right. But now, if the Z2 is gauged, the two vacua are actually the same physical system, and I can find a dynamical way to open a hole in the domain wall. And what you would need to do in that case, of course, simply gauging it is not going to do anything. You need some additional dynamics to open a hole, and schematically, what you need to do is to embed the Z2 into some continuous gauge group. I'm not going to write down the specific details, but now what happens is that I had two vacua from before. They were distinct. There were no way to extrapolate them. There were no way to interpolate between them than going over the hump. That was the reason that domain wall was formed. Now, because of the embedding of continuous gauge group, there might be some other paths. So this is in the continuous group. Where the two vacua can be connected without going over. And what that results in is that you can potentially produce cosmic strings that can open a hole in the domain wall. Or end, the domain wall can end on the cosmic string. Again, I have the domain wall here. It was supposed to be separating phi equals to minus b and phi equals to b. Then this additional embedding in the continuous group says now I can open a hole. We're going through, there's a cosmic string. That's the boundary of the hole. Where what's happening is that, so I have the domain wall and I have a cosmic string. As I go through the domain wall, I'm trying to interpolate the two vacua over this hill. As I go around the cosmic string, I'm trying to circumvent the hill by going through the continuous loop. Yes.
Sorry, I'm a little confused about how the domain wall forms in the first place if you gauge the Z2. Like, wouldn't you just not get a defect at all?
Oh, but still, everything I argued about the fact that you need to continuously interpolate between the field values is still true. Yeah. In principle, you can view it. I mean, not for there. But yeah.
Can I ask a question?
Oh yeah.
Why couldn't you have the string even if it was just
global?
Global, yeah. Why couldn't you have the C2 the domain walls connected by strings so that they would annihilate or disappear?
What would be the
It's a standard way to get rid of the domain wall.
Yeah, there's no actually. So you can try to embed the global Z2 inside, for example, U1. Simplest case to generate, you might imagine generate the string is embedding a U1.
Yeah.
But there is no way actually. So if you embed it in U1, the correct string is formed when you spontaneously break the U1 by a charge 2 complex scalar, which makes sense in a gauge U1. You have a concept of a complex scalar being charged 2, but in a global U1, there's no way to do that. In global U1, I mean, you're always going to break. You try to spontaneously break it, you're going to break it down to nothing. While what you
I don't know. I'd have to think about it, but I would
Yeah.
imagine you've got like U1 cross U1. I mean, there's got to be examples where you could have C2 at the end.
Oh, but physically, I mean, they're supposed to be distinct physical states. So you shouldn't be able to have a zero energy interpolation between two different physical states. That's perhaps the construction independent argument I would give for domain walls being stable when it's global.
But I thought we're trying to destabilize them instead of.
Which means I need to gauge it. If it's global, the only way to get rid of them is explicitly break the global symmetry. If it's an exact symmetry, I cannot get rid of the domain wall. Right. So that's the, if the symmetry is exact, then to get rid of the domain wall, you need the discrete symmetry to be gauged, embedded in some continuous group, such that you generate the correct cosmic string that can attach to the domain wall. I'm not going to go into the specific model building details that you need to do that. But now, so why doesn't this work for parity domain walls? It looks like, to save time, let me just say, now if we come to parity, everything I said kind of here is all true. Now I just have a parity, instead of Z2, I have a parity perhaps that maps a pseudoscalar to the minus of a pseudoscalar. And again, I can write down a potential, and then there will be a domain wall separating two regions that sit in different minima. And I might say, with analogy as internal Z2 symmetry, I want to get rid of the parity domain wall by having parity cosmic string that opens a hole in the domain wall. Now, the central result from McNamara and Rees is that parity strings do not exist. What did I erase?
Tell us about the universe.
Yes, if you have to make choices.
Only 10 minutes. We want to know about the actual universe.
Well, without experimental guidance, I cannot tell you if the model is true or not. As a theorist, it's not my job to say what is the I can say what possibly is the universe. Then the experiment tells us what is the universe. I'm just pointing out experimental consequences. Right. Okay. So this. Let me state the first fact that so when we think about internal symmetry, at this point it doesn't matter if it's continuous or discrete. We always treat, maybe there is a dynamical gauge field. For discrete symmetry there is not, but there is some transition functions or gauge transformation you can define. You think of those gauge configurations as something that you define on top of the space-time manifold. Right? I can say I want to study QFT on a torus. Then I fix the space-time manifold, and now I have a freedom to choose what gauge configuration I want to think about. The gauge, or this, yeah, the gauge configuration is an independent choice of the manifold. Underlying manifold, like Z2 internal symmetry, QFT can be studied on any manifold you want. But then parity is different in the sense that the gauge configuration is defined by the manifold itself. So why is that? It's actually a straightforward fact. If we recall what we know about weird non-orientable manifolds such as the Mobius strip. So if you think about the Mobius strip. Well, it's supposed to be a Mobius strip. So, yeah, so I think it's well known that if I'm a two-dimensional being and I live on the Mobius strip, I raise my right hand and I go around the Mobius strip to come back to where I am. Now I will be raising my left hand. I'm forced to have a parity flip because of the structure of the manifold. I don't have a choice to say, so once I go around the Mobius strip, I cannot say I choose to not undergo parity transformation. I'm forced to do it because of the structure of the manifold itself, which is unlike internal symmetry. I'm free to choose whatever I want, but for parity, I do not have that choice. So let me just, so on the strip, or which is a non-orientable manifold. Going around forces a parity transformation.
Isn't it just that you can't define parity?
I can't define parity non-symmetric theory on Mobius strip. Yeah. If I'm parity symmetric theory, it's fine.
Yeah, so it's parity symmetric.
Yeah. Yeah, but I'm forced. Yeah. That's almost the definition of what's parity symmetric, that you can define it. Yeah. Okay, so that's I suppose it's the central difference between parity and any other discrete internal symmetry you might think of, is that.
So this just, I mean, presumably nobody believes that we live on a non-orientable manifold. So
why don't we let her finish that argument?
But
Because we only have about 5 minutes.
Okay.
Yeah, so I'm not saying we live on a movie
No,
screen. Yeah.
I guess my question just was, this argument, like on an orientable manifold, you can always choose kind of a choice of orientation and parity will flip together because they're orientation. So I don't understand why this argument applies if we live on a oriented manifold.
Oh, if you live on oriented manifold, it simply means, so here, the definition of non-orientation is that I go around a cycle and I'm forced to have the product of gauge transformation, or the product of parity transformation being -1.
Going around cycles in the manifold we live on doesn't force this.
Of course, it does not. But I'm saying the fact that we do not experience parity transformation when we go around in our manifold is a direct consequence of orientability. Right? Once we specify the manifold, I have defined what happens to parity transformation. Unlike internal symmetry, once you fix the manifold, it tells you nothing about what happens to the internal symmetry. You can say I have a theory that I experience a Z2 transformation once I go around the cycle, or I don't experience a Z2 transformation when I go around the cycle. That's the only argument I'm trying to make. I'm not saying that we live here. I'm just saying once we know where we live, we know what happens to parity transformation on the manifold. That's the only statement I'm trying to make. So now let's come back to the destruction of parity, or the attempted destruction of parity domain walls. So recall what we want. Here is the parity domain wall. We want to say that there is a string, parity string, that can end on a parity domain wall. And this way we can get rid of parity domain walls. I'm arguing that this doesn't exist, and it's because, like I said, this fact actually makes it very simple to think about parity string, because I don't really have a choice. Once I know the manifold, I have fixed my gauge configuration. So it's not even like complicated thing about I have to think about all possible gauge dynamics. How do I show that it's not possible to exist? It's actually quite restrictive what parity transformation can do. Okay. Now, what we want is a parity string. I'm just going to I'm going to prove a contradiction that it doesn't exist. So what is a parity string? If it exists. Okay. So it should be a string-like something, a string-like object, such that when I go around the string along a circle, I come back experiencing a parity transformation. That's what we need, because we know that going through the parity domain wall moves me from one vacuum to the other. So as I go around the parity string, I need to experience a parity transformation to come back. So I need a string-like configuration where once I go around, I experience parity. Okay. But what kind of parity transformation can I experience? So we live in 3 dimensions, so we have 3 spatial directions. Since I'm going around the circle, I'm going to do a cylindrical. So the 3, as I'm going around the circle, I have 3 directions, up and down, in kind of close to the string, and outside on the other side of the string, and also front to back. So that's the 3 different spatial directions I can hope to have a parity transformation. But notice that up and down and close to the string and outside or far away from the string, I cannot flip them. Because what happens if top-down coordinate, if I flip the top-down coordinate system as I go around the string? What that means is that I start here. So I have this edge. I start here, I go around, and I come back. And I'm supposed to observe that my top edge has now become the bottom edge. So somehow it's going to be a configuration where I need to glue this side of the cosmic string where these need to be that is not a string configuration. So in the McNamara and Reese paper, they actually study this very weird singularity. It turns out to be a point-like object, which is kind of sensible because you said it's not actually a string-like object. I need to identify the top edge of the string with the bottom edge of the string, which is going to be some weird, it's going to be some configuration, but it's not going to be a string configuration. It's going to be even weirder if you say, now as I go around the string, I want to flip the side that's close to the string to the side that's further away from the string. It's going to mean that as I go around, the string is going to jump from which should be on my left side all the way suddenly to my right side. And that is going to destroy the string configuration as well. Now, so you might say the only sensible direction that I can flip parity is front to back, right? But there's no way to, if you're going around a circle, there's no way to continuously come back that you have turned around. That is a discontinuous configuration, right? Because you are traversing a one-dimensional manifold. There's no continuous way for you to suddenly turn the other way around. You can turn the other way around if you go around the two-dimensional manifold, such as the Mobius strip, right? After I go around in a circle in a Mobius strip, I have somehow turned from right-handed to left-handed. But there's no way to do that when you have a one-dimensional manifold. Okay? So the more mathematical term is just that all closed one-dimensional manifold are orientable. I think this is just a simpler pictorial way to see it. I want to have a cosmic string-like configuration where once I go around, I experience parity, but there's no way for me to experience parity without destroying the object I wanted to have in the first place. So that's the reason parity strings don't exist, and is one certainly. And the parity domain walls are absolutely stable.
Give you a couple of minutes to wrap up here.
Yeah, but okay. The fact, okay, now I came back here. So I have, if you accept my argument, kind of pictorial, but argument nonetheless, the parity domain walls are absolutely stable. There's no way to open a hole on them. There's no way for them to end anywhere. Then the only way to get rid of them, to recover cosmology, is to inflate away. And this is where this consequence comes from. And as I think have already hinted at with discussion with the audience, there is many things that you can observe that shows you that Hubble of inflation is higher than 10 to the 8 GeV. And you can observe a tensor to scalar ratio that tells you Hubble is greater than 10 to the 8 GeV. Actually, you can, if you detect gravitational wave from cosmic string from any of the projected sensitivity of future experiment, you show that Hubble is greater than 10 to the 8. You show that Hubble is greater than 10 to the 8 because to generate sizable gravitational wave, you need to have high scale cosmic string, which means the universe needs to be as hot as that scale. And Hubble of inflation not only sets the scale of inflation, but also sets the temperature of everything that happens after inflation. So there are many things you can observe that shows that Hubble greater, tensor to scalar ratio, gravitational wave from cosmic string. So yeah, no, unfortunately, it's not a spectacular phenomenological consequences. I do not have a single.
Any of those will be quite spectacular, way more so than some Nelson-Barr.
But they would also rule out Nelson-Barr, which is a virtue of the theory, right?
Only a tiny increment of the original virtue of such discoveries.
Okay.
Yeah, I agree, it's incremental, but we need to start somewhere. We didn't, before this, Nelson-Barr literally had there was no way to see where they were at all. Now we have tied it to inflation. Of course, majority of the community cares about measuring the scale of inflation more than proving, disproving Nelson-Barr. But at least it's one connection that resulted from, understanding of parity domain walls that actually required some insights about non-orientable manifold, etc., etc. Thank you.
Well, yeah. have one question. We're gonna take it from him,
Oh.
from Marius.
Okay.
That's a dictator.
That is my title, I think.
I was just a little bit confused about this, like, argument about the point-like objects. So like the up-down symmetry. I'm presuming you mean like as you go around the circle, there's some smooth map of the field configuration, or you map the top to the bottom and the bottom back to the top.
I meant that for a parity, for top-down parity configuration to happen, I'm going to identify this side with that side.
Yes.
And it's not going to be, well, it's a very complicated thing, but it's not going to be a string configuration anymore.
So identify here, you mean like, okay, so I have some like solution to my field equations, some infinite string, and I want to do a parity transformation and see what happens, yeah? And then, sorry, I'm just a little bit confused. Maybe we can talk after.
It just, I was postulating there is a string-like object. Once I go around, I get parity transformation. If you imagine the parity transformation to top down, it would be like saying I go around and once I come back,
It's flipped.
It has flipped, but that's not.
I'm having trouble seeing the inconsistency, I suppose. But
I'm
talk
just
after.
saying that it destroys the original postulate that it's simply a string-like configuration.
So you force some orientation.
I'm forcing my desire to destroy parity domain walls. It required me to have this very specific object, and I'm saying this very specific objects cannot support parity transformation.
Sure.
It can be some weird thing where the top of the string is now glued to the bottom of the string, but that's not a cosmic string.
All right, let's thank Qianshu again. There's cookies and coffee as usual. Thank you. People have a lot of questions.
Oh,
that's
I want to go around this thing.